Our last speaker for the session is going to be Brooklyn Noble. She attends the University of Utah, works in nanotribology, and her advisor is Dr. Bart Raymakers. She's also in her 4th year and also did her practicum at Lawrence Livermore National Laboratory in 2016. And today she's going to tell us about her work on nanoscale mechanics of ultrathin polymer films using molecular dynamics.
Thank you very much for that introduction. So I'll just go ahead and get started. So in case you're not familiar, tribology is the study of wear, friction, and lubrication, and I focus on nanoscale tribology. And ultrathin liquid polymer films are of primary concern in the design of many nanoscale systems and devices because surface effects, including adhesion and friction forces, become increasingly dominant on the nanoscale. Even Nate mentioned the importance of friction. So, for instance, in the medical field, 80% of all microbial infections are caused by contaminated medical devices or implants. However, thin polymer films can be used to modify these surfaces, resulting in inhibited bacterial protein adhesion. Thin polymer films are used in many micro and nanofabrication techniques. There are several examples of this, in one of which semiconducting polymers are aligned along channels in order to create low-cost, flexible electronics. Ultrathin liquid polymer films are also used in many micro and nanofluidics applications. For example, nucleic acids are commonly used in many lab-on-chip devices. Ultrathin polymer films are also used as lubricants, for example, in hard disk drives or in micromotors to prevent wear. My research aims to address the challenges that currently limit the effectiveness of ultrathin liquid polymer films used in a variety of engineering applications. However, my research doesn't focus any more or less on one particular application. Instead, I study the behavior of ultrathin polymer films. Specifically, I study how a nanoscale liquid droplet interacts with the surface. Here I show a demonstration exemplifying the importance of surface effects. An external load is applied to a surface, which dramatically changes how the droplet absorbs and spreads. So you notice that when that substrate is stretched, the red droplet will pin to the surface, and when that substrate is relaxed, it will spread freely. This is an example of an externally dynamically tunable surface. Although crucial to the design and application of ultrathin polymer films, the physical mechanisms that govern spreading on the molecular scale are not well understood, and disagreement between theory, experiment, and simulation remains. My research aims to address these shortcomings and has 3 subtopics: spreading morphology, spreading kinetics, and spreading on nanotextured substrates. So I'll discuss each of my 3 subtopics individually, starting with background and my molecular dynamics model for each. I will show how I quantify spreading morphology and explain my results with functional group layering. I will show how I quantify spreading kinetics and explain my results using the pressure measured in a droplet and molecular entanglement of the polymer. I will show how I quantify anisotropic spreading on textured substrates and explain my results by showing the potential energy created by different nanotextures. So I'll start with my first subtopic, ultrathin polymer film spreading morphology. So the morphology, or the form and structuring of thin polymer films, have been studied using both experimental and simulated approaches. The most common experimental method to study spreading of thin liquid films involves monitoring the diameter of a liquid droplet deposited on a flat surface by a pipette, syringe, or sharp needle while it spreads with time. I show a cartoon of this where a needle that has been dip-coated with a polymer is placed in contact with the surface and then removed, leaving a very small quantity of polymer on the surface. I also show an actual ellipsometry image of a polymer droplet profile from the side, so as if we were to zoom in on the edge of a spreading droplet. One might expect that the droplet would take on a hemispherical cap shape, but this is not what the ellipsometry image shows. Instead, we observe a protrusion in the spreading front of the droplet near the substrate, which we call a foot, and subsequent step-like terrace structures. These foot and terrace structures have been observed in experiments for decades, but have not been explained, nor have they been observed in any simulations. However, molecular dynamics simulations have been employed to study the equilibrium structure of a thin polymer film. I show an example of this where the polymer is contained within a box such that it doesn't spread, and I indicate that functional hydroxyl end group layers are observed in red. So I use molecular dynamics simulations of polymer spreading, where my simulations show for the first time molecular level terrace polymer spreading and how functional hydroxyl end group layers are essential to this phenomenon. So I'll first discuss my polymer model. I use molecular dynamics, which is a simulation technique ideal for studying molecular orientation, bonding, and dynamics over the time and length scales appropriate for this work. I use a coarse-grained bead spring model, which averages atomic interactions for computational simplicity while preserving the essence of the molecular structure. I study perfluoropolyether polymer exclusively. This polymer is widely used in many applications as it easily spreads to a monolayer. It has good stability, low surface tension, is chemically inert, and has a relatively good human body response. There are many types and variations of perfluoropolyether lubricant. I show 2 examples that I study, including their chemical structures and schematics of what both an atomistic and an equivalent bead model might look like. So a polymer is simulated with a number of beads N, where a bead can be thought of as a mirror of a polymer. The backbone of both of these polymers are the same, but they differ in their N groups. The polymer, which we call Z, is terminated with a trifluoromethyl N group, which we refer to as non-functional. And Z-dol is terminated with a hydroxyl N group, which we refer to as functional, because hydroxyl N groups readily form hydrogen bonds and tend to attract. These N groups are accounted for in the bead model, where a functional group is indicated with green. So here I show a typical example of my spreading morphology model. The polymer, which is represented with green and red, first equilibrates between 2 walls, after which it's allowed to spread in the X direction only. The simulation is periodic in the Z direction, so I'm essentially simulating the center section of a droplet as it spreads. A fraction of the top layer of the substrate is blue. Blue represents a dangling bond that a hydroxyl N group, so one of those green polymer beads, would attract to. I vary the polymer length, type, and the quantity of polymer, or the volume of the fluid droplet. So if we were to look at that typical example more closely, we could draw a thickness profile where we would again observe foot and 2 terrace formations like those observed in experiments. Now, the scales here are non-dimensional, but if we were to dimensionalize them and compare to the experimental work I discussed previously, we would observe excellent agreement, so a maximum difference of 6.5%, which is pretty good when you're considering molecular level simulations to macroscale experiments. So here I show all the N beads of the simulation with a black dot, and we clearly observe molecular layering indicated by 3 horizontal bands of conglomerated N beads, similar to the equilibrium molecular dynamics simulations I showed previously. And we also observe that the terrace formations form around the N bead layers. Here I show the N bead density as a function of the y-coordinate, or the distance from the substrate, where each color represents a different quantity of polymer. I also show one example of Z polymer in black. We observe well-defined peaks in the N bead density. For different quantities of polymer, the peaks occur at the same y-coordinate values and are approximately equal to the polymer length. The number of peaks is also observed to increase as the polymer quantity increases, and the magnitude of the peaks decrease as the y-coordinate increases because a layer can only support a layer that is smaller than itself. We also observe that terraces form where the N bead density is minimum, and that Z polymer spreads much more freely, and we never observe terraced or layer structuring. Here I show similar plots of the N bead density as a function of the distance from the substrate for 2 additional polymer lengths. Looking at any single plot, the peaks occur at the same y-coordinate value. However, comparing the 3 plots, we observe that peaks do not occur at the same y-coordinate value for different molecule lengths, and that the distance between peak scales is the square root of molecule length. As a molecule gets longer, they entangle, and they do not stretch to span the gap between layers. We also observe that the magnitude of peaks decreases with increasing molecule length. So in conclusion, N bead layering and terrace formations only form for functional polymer, and that both of these types of structuring are related such that terrace formations form around N bead layers. The number of layer and terrace formations can be controlled with a quantity of polymer, and the locations of terrace formations and N bead layers, as well as the density of N bead layers, is controlled with the polymer molecule length. Thus, if a monolayer film is desired or this type of structuring is undesirable, long polymer molecules should be used. So I'll now go into more detail on my second research subtopic, ultrathin polymer film spreading kinetics. So the spreading kinetics of polymer films have been studied using both experimental and simulated approaches. And it is well known that during spreading, the droplet radius r increases with time t according to a power law. However, both experiments and simulations document widely varying and sometimes seemingly unrelated values of the spreading exponent nu. Tanner's law, diffusion theory, and the microscale droplet theory are a few examples of theories that predict different values of nu based on different physical considerations. In general, however, experiments of droplet spreading do not report a uniform value of nu. Instead, the spreading exponent varies over a wide range or with multiple distinct spreading regimes, typically with an initial fast spreading regime followed by a slower one. I show an example of this. This is an experimental result. The droplet edge radius is plotted as a function of time on a logarithmic scale for two droplets of different size but that are otherwise the same. Because the scale is logarithmic, the slope of the straight line is the spreading exponent nu. We'll observe that the larger droplet initially spreads with a speed close to that predicted by the microscale droplet theory and transitions to a spreading speed close to that predicted by Tanner's law. I should point out that the solid markers indicate that a central droplet is present and hollow markers indicate that the central droplet has depleted. So essentially comparing those two 3D images on the upper left corner, where the leftmost one would have a central droplet and then afterwards it would deplete to a monolayer. So we define a central droplet as anything more than a film foot thickness or a monolayer thickness. For the smaller droplet, the central droplet depletes much faster and only a slower spreading speed is observed. Although the transition between spreading regimes has been linked to the central droplet, it is not clear why this is. It is also not clear why different theories dominate for different experiments or during different times of the same experiment. With the aim to provide a unifying explanation, I simulate polymer spreading on the molecular scale over a wide range of design and environmental parameters. So here I show a typical example of my spreading kinetics model. However, as opposed to the previous simulation setup, polymer equilibrates within a cylinder, which represents a pipette used in experiments. And the substrate is large enough in both the X and Z directions such that the polymer has ample room to spread. In the previous setup, the polymer only spread in the X direction. I vary the functional substrate fraction between 0 and 100%, such as the substrate is either fully functional or non-functional. I also vary the polymer type and polymer length. So I quantify spreading kinetics by looking at the edge radius as a function of spreading time. On a logarithmic scale, again, the slopes of the lines are the power law spreading exponents. Similar to the experimental results I showed earlier, solid markers indicate a central droplet is present and hollow markers indicate that the polymer has depleted to a monolayer. I only show the most extreme cases, and I divide these extreme cases into 3 categories based on the spreading kinetics that we observe. So for the first case, we observe one spreading speed of 1/3. We observe this for short molecules that can be functional or non-functional polymer on a non-functional substrate. In the second case, we actually observe a transition observed in experiments. So initially, the polymer spreads with a speed of 1/3, similar to the previous case, but then transitions to a spreading speed of 1/10. We observe this for any long polymer. It can be functional, non-functional, or on any type of substrate. And the third case has one spreading speed of 1/10. This is only observed for short molecules that are functional and on a functional substrate. So to explain the drastically different spreading kinetics observed, I quantify pressure throughout the droplet as it spreads. I show pressure maps from the side, created by averaging about the cylindrical angle, where red indicates high pressure and blue indicates low pressure. I plot the pressure difference as a function of time, essentially comparing the high and low pressure regions when looking down at cross-section AA in the upper left corner. So let's look at each case again. For the pressure-driven flow case, or that first case when we observe a spreading speed of 1/3, the pressure decreases immediately along with the central droplet. In the second case, when we observe a transition, again the pressure decreases with the central droplet, but unlike the previous case, a competing mechanism exists that acts to slow spreading. This is why we call this pressure-driven but entanglement-inhibited flow. For the third case, when only a slow speed is observed, the pressure remains high, as well as the central droplet does not deplete. Pressure acts to drive spreading, but cannot overcome the functional end beads pinning to the fully functional substrate. So we call this pressure-driven, chemically inhibited flow. So to explain why some simulations exhibit a transition in spreading speed, but some do not, I quantify polymer entanglement. I define the entanglement index as the average number of beads that remain within a close proximity for at least a set period of time. I plot the average entanglement index with time and show top view maps if we were looking down as the droplet spreads, where red indicates a lot of entanglement and blue indicates a molecule is completely isolated for an extended period of time. So for the first case, when we observe a spreading speed of 1/3, the entangled center quickly untangles because molecules are short and spread freely. In the second case, when we observe a transition, the droplet largely untangles, but regions of entangled knots remain. This acts to resist spreading, and when the central droplet depletes, becomes a dominant mechanism that will inhibit spreading, and this is why we observe a transition. The third case, when only a slow spreading speed is observed, the entangled center remains due to the attraction of functional groups to the substrate, and only the outer foot region untangles. So, in summary, we observe 3 spreading scenarios where either the microscale droplet theory or Tanner's law will dominate, depending on the substrate and polymer parameters. We attribute these differences to competing physical mechanisms. 1, a pressure gradient in the droplet that vanishes if the central droplet depletes. 2, entanglement, which is dominant for long molecules when the central droplet depletes. And 3, attraction of functional molecules that pin to a substrate, which is dominant for short functional molecules. In conclusion, we were able to show why the presence of a central droplet can significantly modify spreading behavior and why this does not always occur. In addition, we were able to show the underlying physical mechanisms and explain why different theories dominate under different circumstances. I will now go into more detail on my third research subtopic, ultrathin polymer spreading on nanotextured substrates. So there are many examples of textures altering wettability in nature. I'll discuss 3. The lotus leaf has a low adhesive force because its texture creates an air cushion such that droplets can easily slide off. A rose petal has a strong adhesive force because its texture is easily infiltrated such that droplets pin to the petal even if the petal's turned upside down. And the pitcher plant is omniphobic, so it repels most things because its texture is infiltrated with a lubricant with a high affinity to the substrate so that it spreads to a monolayer, such that external liquids have a low adhesive force and easily slide off. Altering the wettability of a substrate has many potential applications like self-cleaning, anti-fogging, and anti-fouling surfaces, but textured substrates can also be exploited for other purposes. For example, anisotropic spreading finds application in micro or nanofluidic devices, flexible electronics, and drag reduction surfaces. I show an example of a unidirectional nanotexture that creates anisotropic spreading, where the droplet spreads preferentially along the texture. Anisotropic spreading on unidirectionally textured substrates is most commonly explained by the texture peaks, which impose a mechanical barrier that inhibits spreading in the direction perpendicular to the texture and squeeze the droplet to spread parallel to the texture. I use molecular dynamics simulations to develop a molecular level explanation of how nanotexture features affect polymer spreading behavior and how this is affected by texture peaks and texture grooves, the texture feature shape, and texture feature size. So here I show again my model where polymer spreads on a rigid substrate, but this time with a unidirectional sharp nanotexture. This is very similar to the previous task except for the change in substrate. For this subtask, I only vary the texture feature size L, which is the distance from a peak to a groove, and the shape, which can have a defined angle theta, like the example I show here, or a sinusoidal wave shape, where the width divided by the height defines the aspect ratio. So I start with showing the polymer spreading behavior in a single groove for 4 examples: a 60-degree groove, a 90-degree groove, a sinusoidal wave groove, and a flat substrate for reference. For each groove geometry, I show a side view and a top view. I also show the spreading both parallel and perpendicular to the groove, plotted as a function of time. Red squares show the spreading along the groove, and black triangles will show the spreading perpendicular to the groove. So let's start with looking at the flat substrate. Looking at a top view, spreading appears omnidirectional, as you would expect, and no directional spreading is observed, as expected. Now comparing, for the 60-degree groove case, the top view shows drastically more polymer spreading along the groove, and that this polymer appears well aligned with the groove. The polymer indeed spreads more than twice as much along the groove than perpendicular to it. For the wave groove, the top view suggests directional spreading as the droplet shape appears oblong. However, if we look at the true spreading in each direction, they are nearly identical, thus no directional spreading is observed. For the 90-degree groove case, we observe polymer alignment at the groove and a slight spreading advantage in the direction along the groove. So the last slide showed the case when the texture length was long, such that only one groove was encountered. I now look at the effect of multiple texture features, which include peaks. I plot the polymer spreading both parallel and perpendicular to the unidirectional nanotexture as a function of the texture length for various texture feature shapes. We observe that textures with similar groove shapes yield similar parallel spreading results despite different peak shapes. We also observe that textures with the most negative minimum energy yield the most spreading parallel to the texture. For example, textures with 60-degree grooves yield the most negative minimum energy and also the most spreading parallel to the texture, regardless of the texture peak shape. Here they either have 60-degree peaks or wave peaks, but that doesn't really seem to affect it. Wave-shaped grooves yield the least negative minimum energy and also the least parallel spreading, regardless of the texture peak shape. You will also notice that for wave-shaped textures, especially the case with the smallest aspect ratio, the parallel spreading is not independent of the texture length. This is because the minimum potential energy created by wave textures also varies with the texture length. For textures with a specific angle and minimum potential energy, so everything with a defined angle, spreading parallel to the groove is independent of the size of the texture, such that these lines are horizontal. Comparing the two plots, we observe that polymer typically spreads much less perpendicular to the texture than parallel to the texture. Note the different y-axis scales. We also observe that spreading perpendicular to the texture decreases with decreasing texture length, and this is more pronounced for textures with sharp grooves. For example, textures with 60-degree grooves yield the least perpendicular spreading despite different peak shapes. So to explain why the groove shape seems to be the dominant factor that determines polymer spreading on textured substrates, I show 4 examples where potential energy and polymer quantity maps are shown as if zooming in on both a peak and a groove for each substrate. So from the insets on the right, we observe dark blue regions in the grooves where the attractive energy potentials of multiple substrate beads superimpose. We also observe that polymer beads cluster in these regions to minimize their energy state. From the insets on the left, we know that the polymer quantity locally decreases at texture peaks because the attraction of fewer energy potentials exist, and polymer molecules avoid these regions to minimize their energy state. Here I show parallel and perpendicular spreading as a function of texture shape and the corresponding minimum energy on the right axis. We observe that parallel spreading corresponds to the minimum energy and that the perpendicular spreading inversely relates to the minimum energy. Thus, spreading both parallel and perpendicular to a texture is determined by the shape of grooves, not peaks, as what has been thought previously. Sharp grooves both inhibit spreading perpendicular to a groove and promote spreading parallel to the groove, completely independent of the peak shape. This is because the texture groove shape determines the minimum potential energy created by a texture. So for applications with textured substrates where controlled wetting is desired, sharp grooves can be exploited. However, in order to create a uniform monolayer polymer coverage on a substrate, it's not the size of the feature that controls coverage, but the sharpness of the peaks. Thus, sharp peaks should be avoided because polymer dewets sharp peaks. This work has resulted in 5 journal publications and 4 oral conference presentations. Now, before I take questions, I would like to take a moment and thank everyone who made this experience possible for me. Not only did this fellowship provide excellent financial benefits, but it also provided amazing opportunities. Like it was mentioned, I had the opportunity to intern at Lawrence Livermore National Laboratory. I've also had the opportunity to make friendships and connections that I'll take with me wherever I go. I've truly been so honored to be part of this talented community. And with that, I'd like to take questions from the audience.